Okay, so let's do some geometry here. So what I'd like you guys to do is draw the molecular structure, the Lewis dot structure of the compounds. Okay. How many minutes? You think you need, what, 15?
Like 30 an hour.
Yeah, right. What are you smoking?
Nothing right now.
Nothing right now. Good. Okay, you gotta wait till after class to do that. Let's see. Okay. Gonna give you something in the middle. Got 18 minutes. You guys finished early? Come on out. What was that?
What we're doing, I just got on.
So you guys are drawing the Lewis dot structure for all 5 of these. You're telling me the electron pair geometry, and you're telling me the molecular geometry.
Okay.
Okay?
All right.
All right. Are we ready?
Are we going on group?
Yes, you're going in groups.
Okay.
Oh, you're just going to tell me, huh? Let's see. I have to shift some groups around, though, because I have a tutor. Where are my other tutors? They're slacking. Let's change. Okay. And then I'm going to make. Okay, ready? Rooms are open. Good luck. Let's see. Elizabeth group, you guys have CO2. Rocky's group, you guys have H2S.
You're missing CH4.
Thank you. I was working. I was trying to figure out what was the last one I put up there. Let me save it this time. Thought I saved it the last time.
H2S. Oh, you got that one.
So Fabian's group, you guys have BF3, and Heidi's group, you guys have CH4. Is that what you guys discussed, Fabian?
We're missing 2, Fabian. I just don't know from where.
Wait, hold on.
Are you confident in that answer?
No, this is the only one that we were working on right before you took us back.
Oh.
I was hoping you'd give us like CO2. We're missing 2 somewhere.
Yeah,
Oh, yeah, we were. Wait a minute.
2, 4, 6, 8, 10, 12, 14.
Okay, now think about the rule. Who's top dog? Who is the bully on the block? Who is the king of the castle?
Fluorine.
Everybody bends to his will. Come on, Fabian, you should know this one.
Fluorine?
Fluorine. So is fluorine going to be the bitch in the middle?
Oh, that's my bad. That's my bad. That was me.
Yeah, boron goes in the middle because it's furthest from the noble gas.
That is correct.
But I thought boron was a whore. Like they could go give and
No.
take.
Carbon. Carbon's the whore. Now get your terms right.
Dang, that's my bad.
2, 4, 6, 8.
Okay, yeah, we got it that way.
And then if you think about it, a whore is going to try to make whoever's happy, right? Because
Yeah.
she has to get paid, or he has to get paid, you know? Men and women can be whores, you know? So they're going to make whoever happy. So they'll gladly be in the middle, you know?
Oh.
I'm sorry if you have kids in the background. I apologize. I keep forgetting that
Oh,
we have
yeah.
children around.
I'm sorry.
I'll change my terminology there. So, good job. Good change. Good change. Good change. Okay. Let's see. Yes. Let's put the info. Good job, group 3. Although group 3, I mean not group 3, group 4, Heidi's group, or group 5, Heidi's group. So you said its electron pair geometry is tetrahedral, meaning four sides, 4 attachments. What about its molecular geometry? Or is this, wait. The stuff in blue, who is that for?
I think that's ours, right? This one. Professor, is that ours? I don't know.
I don't know. I mean, this one right here? Oh, this is Iberi's. Oh, this belongs here, underneath here, right? Iberi? Okay,
Which one?
Iberi. So you gave me the electron pair geometry. You said tetrahedral. And then is it called the electron geometry, or is it called what?
Molecular.
Molecular geometry.
Molecular geometry.
So, Professor, which one were we supposed to do?
Your group, Rocky, you guys have your number 3. So you're H2S.
So let me quickly do it. H2S. So for this.
Good job, Fabian. Fabian's group. Trigonal. Good job.
Good job, baby. Way to carry the team.
Good job.
It was a
baby.
team effort.
I like hearing that. What about this guy over here, CO2? That's Elizabeth. What is the electron pair geometry for that center atom? Come on, Eric. I know you're at the beach, but still.
What was that?
You guys haven't finished.
Oh,
You got 2 more things to answer for me. Erica, don't think you're out. Roke, come on.
Which one are
Miguel, you guys are CO2?
Oh, okay.
So what did you guys get, Rocky? What is your answers? Finish it up. And Heidi, You got the electron pair geometry. What about the molecular geometry?
Hmm.
Heidi's team. Do you guys introduce each other? Do you guys know who you're talking to in the group?
Yeah.
Kelsey?
We did.
We did.
What did you say? Wait, sorry, I wasn't listening.
I said, do you guys talk to each other in the group? And it said, do you guys introduce each other? Do you guys know each other's name?
Yeah,
Okay, I'm just asking.
you popped in all mad.
Who, me?
Yeah, use your
Yeah, I
I'm
know.
not
And the first,
mad.
and the first guy,
I
Eric.
didn't say nothing.
Eric, why don't you have your whiteboard out?
Yeah, he started yelling at me too.
You act like you're new to Zoom.
Exactly. That's exactly it. You act like y'all are virgins. Y'all ain't virgins.
Oh yes.
Yes, I am. I'm holy.
Yeah, right. And I'm the Pope.
You're a cardinal. You're in red. Hey, are you mad?
Oh my goodness, he's wearing the red shirt.
Are you
Oh.
mad, Dr. Henry?
Yes, I had
He's
my
mad.
class, and I'm grading their test. They want me to start drinking early.
No bueno.
And it sucks because, you know, they do like half of them get one half, and then the other half get the other half. If they just kind of communicate with each other, they'd have the full thing. Let's see. Okay, let's see. Good job. Okay, so let's see. So we have for the electron pair geometry for ammonia in the middle. That's correct. So those are correct answers there. Electron and molecular geometry is also correct. For the methane, it's also correct. For hydrogen sulfide, that is correct. CO2, let's think about this. So it has how many atoms attached to it? Are there any lone pairs on that center atom?
No, it should be linear.
Should be linear. So just a reminder, when we're looking at our geometry, we're looking for lone pairs. Lone pairs counts as an attachment for the electron pair geometry, right?
Mhm.
If it has no lone pair and it's only attached to another atom, so that counts as one attachment. Here, this counts as another attachment. So then all you have is a straight line.
Mm.
So that's linear. And then the molecular geometry, there are no lone pairs to kind of shift it or shape it. So on that center atom, so again, this is going to be linear.
So when do the lone pairs count again? And
Lone
which one?
pairs count only for the electron pair geometry. They also kind of shape our molecular geometry. Like for instance, here we have the molecular geometry is trigonal planar. There's 3 attachments. That gives me my trigonal. Trigonal pyramidal. There's 3 attachments. And then we have the lone pair that helps push those guys down. So they're looking like a pyramid. Okay. And so, Rocky, I'm going to move your stuff over here. You guys have it. You had the work over here. Okay, so the electron pair geometry is going to be tetrahedral for this guy, and it's going to be bent because you have 2 lone pairs, and then you have those 2 attachments. So it's called a bent shape. And Fabian is right on point here. So it's trigonal planar because you have 3 attachments, and so your angle's all going to be 120. And it's all in the same plane, so it's like flat, like a widget spinner. Those 3-pointed widget spinners, or fidget spinner, whatever it's called. Okay.
I have a question.
I may have an answer.
On that BF3, the boron there, it has only 6 electrons.
That's right. What do we know about boron? Boron and Be.
They like to share.
They like to share, or they're weird?
Sorry, they are weird, yes.
They're weird. So they always have what we call hypovalency. So boron is only going to have 3 around it, and it's cool with having 3 around it. And beryllium, which is technically a metal, doesn't want to act like a metal, so it shares electrons, but it only wants 4 around it total. So boron will have total 6 electrons around it, and beryllium, Be, will only have 4 around it.
You said boron only have 6?
Yep. Boron will only have 6 around it, and Be will only have 4 around it. So Be will make 2 attachments, and boron will make 3 attachments. So, and it's always like 90% of the time, 99% of the time, it's going to be we call hypovalent.
Hypovena.
Hypo meaning under. Like hypothermia, under temperature.
Uh-huh. Hypovalence. Okay.
Yeah. Yeah. Okay.
Okay.
So who's going to form hypervalence?
Hyper, anything from
Mm,
those ones after group 3.
That's right.
From group 3, yeah.
Okay. Questions, concerns, Cash?
What was that again, Dr. Henry, on hypervalency?
So who's going to form hypervalency?
Those will be like
Is that
aluminum.
the block that we had talked about before, from aluminum down to, all the way down to the NH?
Is it aluminum?
Uh,
Pull up a periodic table.
Well, one of them is phosphorus.
I thought aluminum across to argon, and then that block all the way down to the bottom.
Ah, so you're saying the 3rd row? Yeah.
Yes.
So
Yeah.
the third period. So you're saying the ones in the third period, right?
Yes, that's what we're thinking.
Okay, that is correct. Third period and down.
Yeah.
That is
Those will
correct.
be the hyper. Okay.
So these guys,
Which ones?
third period and down. So that's like silicone, phosphorus, sulfur, chlorine, and then all the guys that are beneath them.
So,
So this block.
so doctor, does that exclude aluminum?
What was that?
Never mind.
Aluminum doesn't typically do hypervalency. I mean, it can technically, but usually if it does it with complex ions, but not so much with,
Okay.
because aluminum is really it's a transitional metal. It's a post-transitional metal.
So we have that to where now? Please, I need to know.
What was that?
So we have from silicon to, because I can't see it very well. Silicon to where? To,
See all of those right there? Let me make this better. So your metalloids
okay.
are included in this area. You see those guys that are boxed? Silicone all the way down to astatine,
Okay.
okay? And that's not including your post-transitional metals,
Okay.
okay? Okay. Questions, concerns, Dash? Okay, you guys are doing great. You already started out on the right foot. Let's go through this lecture, get this done. Get a little OChem in our blood. Okay. So we went over this. I think we went over this the last part of the lecture. Actually, we were all the way here. So I remember going over this. So this is the table that you guys need to make reference to. Okay. So you want to be sure that you understand this table, because I guarantee you're going to have at least 4 or 5 questions on your exam, which is going to be coming up in about a week and a half or so.
See anything?
What was that? Oh, you don't see anything.
I'm looking at you.
It's because I'm so cute. What can I say? I like showing my face. What can I say? Come on, you at least can agree with me. You guys are hard.
I think this is the first time we've actually seen your whole face.
Oh, really? Because usually it's just the top of my head.
Yeah.
Yeah. Yeah, it's because I've adjusted my levels here.
So this is the
Okay.
thing you're talking about?
Yes, this is the table I'm talking about. And if you actually look at it, yes, look at that beautiful table. That is a beautiful table, Megan. Right? And if you actually look at that table, isn't that in your resources? So really, if you understand how to use the table, there is no reason that you should be getting the answers wrong. Is that correct?
Mhm.
Yeah.
Something we're to be able to use on the test?
Was it in the resources?
I just got mine from the PowerPoint.
Yeah, but I believe I have it in the resources as well. Check to be sure. I could be wrong. If not, ask me to put it up. I can be bribed.
It's there.
Can you put it up?
Please.
I can be bribed.
Please.
No, but beware of how to use it.
The
Right.
girls need to ask them. That's why.
What was that?
The girls got to ask you.
Yeah, Eric, you asked me, I'm going to say no. You know that. Okay. So we've also talked about the dash wedge structures, right? You're going to have maybe 1 or 2 questions on that. You just need to know. The biggest thing is the Wi-Fi signal means it's going in back. This guy is going in front, right? And so all it is to try to give us a 3-dimensional looking at an element, right? And that's it. Okay?
Got it.
And then if it's planar, if it's trigonal planar, like these center atoms, each of these center atoms is trigonal planar. You don't have to worry about something going in the back or something going in the front. It's all in the same plane. So you just draw it flat, like a piece of paper. And that's what this is. This is just a flat drawing. Okay, let's talk about polarity. We're going to talk about molecular polarity. So,
Dr. Henry?
Yes.
Wouldn't that last, what was it, the model that, or the one that you showed us right now, where you said it was trigonal planar, wouldn't it be tetrahedral? That's 4.
How many attachments does it have, this carbon?
Oh, okay, no, never mind.
So because it shares a central atom, that's what you're going off of?
Yeah, so you go with each center atom,
Gotcha.
right?
Professor, please come again. I didn't get that.
I said that you want to go with each center atom.
Oh, okay.
Okay, so when we talk about molecular polarity is the polarity of the whole molecule. You know, we've already talked about the bond polarity. Now we're taking into consideration the whole thing. So you're taking into consideration all the bonds all together that are there. Okay? So let's see. So first we've got to understand symmetrical. Symmetrical basically means that we're looking at symmetry based upon the axis, right? So like for instance, if we look at this axis here, let's say this is our axis. So these guys are symmetrical to each other because they both have fluorines on both sides.
They mirror each other.
Exactly. If we look at the axes here, they're symmetrical to each other, right? So this guy has symmetry on both sides. It's also nonpolar because all of the sides are being pulled evenly. So.
Non-polar only applies to symmetrical things.
Well, yes, for the most part.
Okay.
There, I will show you some exceptions here.
Okay.
And in order for it to be symmetrical, it has to be on both the X and Y axis, correct?
For the whole thing to be completely symmetrical. So you could be symmetrical on a single axis, right?
Okay.
So there is a possibility of that because we're talking about more, you know, we're not looking at just a single center atom. Like in this case, we're looking at 2 center atoms in that case. Just so happens it's symmetrical on both sides, okay? Okay, so polarity, polar molecules are going to be asymmetrical, okay? And that basically means that it has that positive and a negative pole associated with it. So the more electronegative atom is going to be pointing towards, let's say, the positive plate, and the less electronegative atom is going to be pointing towards the negative plate. So really what you're doing, you're looking at a field. So you're kind of making an electrical field. And I'll show you this in a second. And I'll give you an example. Okay? So in the case of things that are symmetrical, or in the case that there is no polarity overall, we have like atoms like CH4 and CCl4. I'm going to show you that, where these guys are considered to be asymmetrical. And then let me show you a diagram so you can actually see it. Okay, so if you look at the bonds, individual bonds, So the bond, this is carbon. This here is Cl, right? So who is more electronegative, carbon or Cl?
Yeah.
So that means that the electrons are pointing towards the Cl, meaning that the electrons are spending more time on the Cl side than they are spending on the. So this is kind of like, here you have quadruplets that is taking one arm, taking the other arm, taking a leg, and taking a leg, and they're all pulling evenly, right? So is any of them going to pull you towards them, since they're exactly the same? They have the same strength. They have the, So in that case, because it's all being pulled evenly, right, and it's being pulled away, so then in that context, there's no net dipole moment. So there's no polarity. So it's nonpolar. So this is a nonpolar molecule. So it's molecular polarity. Okay? Spell, let me type it.
So Professor,
Yep.
you remember how you told us that we can subtract the electronegativity value from the other? Does that work in this case?
No, it's only because you're looking at, in that case, you're only looking at the bond. Here, you're looking at the whole molecule. So if you look at the whole molecule, that you're talking about each bond, right? But you're looking at it as a whole in this case, right? Okay, so here, this is hydrogen. These are all chlorine. This is carbon. So who has more electronegativity? Chlorine or carbon?
Chlorine.
Chlorine. Okay, so in that case, each bond is going like this. This one is going like this. And this one is going like this. Right? So this guy, right, because he's weaker than each of those chlorines, the electron is going to be spending more time with the chlorines than they are going to be spending with the carbon and also with that hydrogen, right? So overall, if you look at the net charge, it's going to go between them. So let me draw that in a different color. So the green represents the total net charge. So it'll be going towards where all the chlorines are at. So if we look at it like this, looking for okay. So we have Okay. So can you guys see my screen? Let me stop sharing. Can you see my little glow sticks that aren't glowing? Okay. So there's 3 of them, right? And then I have the one up here, up top. Okay. So in this case, this guy, this red one here up top, that's going to be like your hydrogen. These guys are going to be your chlorines. So your chlorines are pulling the electrons towards them. So the net pull is going to be going in this direction between the chlorine. So do you guys see that?
Yeah.
Okay. So that's what that's showing.
So it's just going towards the more electronegative.
That's right. The ones that are the most electronegative. Exactly. You got it.
And so that would be the net pull?
That would be the net dipole. Yep. Okay, so here we have 2 hydrogens, the white ones. The 2 yellow ones are chlorine. So in this case, the net dipole are going to be between those 2 chlorine.
So it can be symmetrical, is that why?
So in this case, it's not so that it's symmetrical, but it's just because the electrons, the chlorines have more electronegativity. They're going to be pulling the electrons in that direction. So it's going to lack symmetry. So that one won't be symmetrical, right? This guy is symmetrical, but these guys are. Okay, and then this guy, since you only have 1 chlorine, so in that case, it's all being pulled towards that 1 chlorine. Okay, and here we have only hydrogens, and so they're all pulling evenly, and so there's no net dipole. Piece of cake?
So that CH4 and CL4 is having the same net dipole.
That's right. Yeah, for different reasons though, but yeah.
Okay.
Okay, so if we look at triatomic 3-atom molecules, so if we have carbon dioxide, so this guy also has no net dipole, right? Because in this case, they're pulling away from each other evenly.
Like a
That's
balance.
right. That's right. Okay. Where this guy, where the red is the oxygen, these are your 2 hydrogens. So they're both, the electrons are going both towards the oxygen. So your net dipole is going to be going towards your oxygen.
So
So your H2O wouldn't be symmetrical,
Yeah, that's right. H2O is not symmetrical.
even though it looks symmetrical. It goes off of electronegativity.
Yeah.
Gotcha.
Where your carbon dioxide is.
Right.
Okay. Questions?
Which one is asymmetrical? Did you say asymmetrical or symmetrical? I don't know.
Is it polar?
The water, H2O,
H2O is asymmetrical.
asymmetrical. Okay, that's what I need to know. And this one is symmetrical.
That's right.
Thank you.
Okay? Questions, concerns, Cash? Okay? Organic chemistry, are you guys ready? Now that you've kind of learned, you've learned a little bit about geometry. Organic chemistry uses a lot of molecular geometry, okay? So I'm gonna give you the definition of organic, and then I'm gonna give you the definition of inorganic. Now, organic is basically the study of compounds that have carbon in them, okay? Now, it depends on who you talk to, right? But for the most part, any compound that has carbon in it is considered to be organic, okay? That is the very general definition. Now, inorganic compounds are molecules that don't have carbon in it, okay? Now, there is debate because we have certain molecules like carbonate. Carbonate is CO3. The carbonate ion. And then cyanide is CN. And then just oxides of carbons, okay? And then there's a few other ones that are carbon containing compounds. And then so sometimes they're not included in or included as being organic. For generally, for our purposes, for the exam purposes, what you guys are gonna do, so anything that has carbon in it, we're gonna call as organic. Now, we have a special case of organics called hydrocarbons. Hydrocarbons. Look at the name.
Hydrogen and carbon.
What was that?
Hydrogen and carbon in it.
Hydrogen and carbon in it. So if it has only hydrogen and carbon in it, it's a hydrocarbon. So if I have this guy, is that a hydrocarbon?
Yes.
What about this guy?
No.
What about this guy?
No, I think it's only when it has hydrogen and carbon in it.
That is correct. So this is not a hydrocarbon. 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 This is the only hydrocarbon here.
Like methane,
It only
butane.
has hydrogen and carbon in it.
By themselves?
What was that?
When it has hydrogen and carbon by itself?
That's right. Just hydrogen and carbon. There can't be oxygen. There can't be nitrogen. There can't be beryllium.
Like that, those ones who might have butane, methane, all those.
Okay. Are we good so far?
Hydrocarbons are organic.
Hydrocarbons are organic because they have what?
Carbon in it.
Carbon.
Because they have carbon in it. Okay. Whew.
All right.
Okay. I'm good. I'm good. I just need a Red Bull or
I've had
A shot.
and a shot. Yes, and I'll be great. Okay, let's see. So we've talked about hydrocarbons. Now let's talk about specific type of hydrocarbons. So we have 3 major hydrocarbons that we're going to be talking about. I'm going to give you some general information about it, and you're going to have to write this down because it's going to be on the test, okay? So we have what we call an alkane hydrocarbon. Okay, so now these hydrocarbons are all single bonds. So alkanes are, let's say for instance, we have methane. Okay, so I'm going to give you some roots that you guys are probably going to write down on flashcards if you're smart. So meth, or met. We have eth. We have pro.
Propane, ethane, methane,
We have bute.
butane,
We have pent. We have, and then it just go pent, hex, hept, oct,
Sept.
Oh, I know.
known, and then we have dec, and then un dec, do dec. Okay, so meth, that's one carbon. Eth is two carbons. Prop is three carbons. Bute is four carbons. Pent is five carbons. Hex is six carbons. Hept is seven carbons. Oct is eight carbons. Known is nine. Dec is 10 carbons. Undec, 11 carbons. Dodec, 12 carbons. Okay, you got it? Okay, so if it's all single carbons, I mean single chain hydrocarbon, so if I have C, okay, so what would I name this guy? So this guy is called methane. So this guy is going to be called,
ethane gas,
what was that?
ethane gas,
Ethane.
For sure.
Okay, so if I have three carbons, and you'll see that it's saturated with
1, 2, 3.
hydrogens. So when you're talking about saturated fat, that means that you have only single chains or single bonds.
yeah,
Okay, so 3 carbons is called
Propane gas. Propane.
propane. Piece of cake?
Mhm.
Yeah.
So if I had 7 carbons, what would it be called, Rocky? Are you there, Rocky?
I'm
Uh-huh.
here. Okay.
Hept what?
And
Heptane, that's correct.
Heptane. Okay. I don't know.
Help, that's the way to help out, Eric. Good job.
Thank you. Thank you for helping me out.
anytime.
Okay, Elizabeth, if I have 11 carbons and they're all single chains, or single bonds, not single chains, single bonds.
Undecane.
On decane, correct. Good job. Okay, you guys get that so far?
Yes.
Okay, so let's make it a little bit harder.
Go for it.
Okay, so I'm gonna move this over. Okay, so if I have a double bond, just one double bond, that becomes an alkene. So at least a double bond.
Hydrocarbon.
In the hydrocarbon chain. So if I have okay, so this guy would be called
Ethene.
Mhm.
okay. So if I have
Butane.
that's right, butane. Was that Matt?
Me, Eric.
Eric. Oh, awesome, Eric. Good job.
For the on the exam, how would you ask these questions? Just find the hydrocarbons.
I'd write the chemical formula,
Mhm.
and then I'd say, is this an alkene, an alkyne, or an alkane?
Oh, okay, okay.
And then I say, hey, name it.
Mhm.
Dr. Henry, can you
Yep.
explain,
What was that?
explain why it's a butene?
It's butene. How many carbons do I have?
There's four.
4.
I heard somebody say 4, right? 1,
4.
2, 3, 4. So it has 4 carbons. So that's bute and ene, E-N-E, is if there's at least one double bond. Is there a double bond in here?
One.
Okay, got it. I just didn't know how are you getting the E-N-E?
Yeah.
Or where are you getting it from?
Yeah. So if it's all single bonds, we put A-N-E, right? If it has a double bond in it, we put E-N-E, okay? Now if it has a triple bond in it, let's see.
With the Y? Ye
Yep. So
butane. Something like that.
oops.
1, 2, 3.
Okay. So what would that guy be called?
Propyl.
So I guess I should tell you how you name it. So if it has triple bond, so alkyne
Procan.
has at least
Fine.
one triple bond. Okay, so is there one triple bond in here?
Yes.
Yeah.
Okay, so what would I call this guy?
Propine.
Propyne. Okay, how you feeling?
Good.
Good. Okay. So you're probably going to ask me at some point, can I have a double bond and a triple bond and a single bond all in the same structure? And yes, you can. So in that case, certain ones have priority over each other. Okay. And we'll talk about that priority. What are we doing on time? Yeah. We'll talk about that priority next, our next lecture.
Could I get a guess?
What was that?
Could I give it a guess?
Yes, you can give it a guess.
Would it be the carbon with the carbon with the most bonds?
The carbon with the most bonds.
Yeah.
Actually, it used to be that. They actually recently changed it so that it's the second, the double bond has priority
Oh, okay.
over the triple bond. And then the triple bond has priority over the single bond. So single bond is low man on the totem pole, and then everybody else builds up off of that. Yeah, it's weird because when I learned organic chemistry, the triple bond had priority over the double bond. And that it makes sense that way. But
why did they switch it to make
I
it
have
more
no idea. In all honesty, I think it's because triple bonds they're not as stable. They exist, but they're not as stable. So there's only a few molecules that will actually have them. Double bonds are more stable. And I think since you have more abundancy of double bonds than your triple bonds.